The world is made of things we cannot see, and yet they shape everything. In the depths of matter, beneath the surface of atoms, below the familiar realm of molecules and cells, there exists a place where the very fabric of reality becomes something else entirely, something strange and beautiful, a realm so small that light itself becomes a clumsy tool for observation, a domain where particles dance in patterns that defy the everyday logic we carry through our waking hours. Tonight, we descend into that hidden architecture, the quantum world where the fundamental pieces of existence reveal themselves, not as solid objects, but as fleeting probabilities, as whispers of energy, as moments of interaction that build the universe from the ground up. This is the realm of particle physics, a landscape populated by entities with curious names, quarks and leptons, bosons and fermions, each one a thread in the tapestry of everything, each one governed by forces that operate beyond our direct perception. And yet, these invisible actors perform on a stage that determines the color of stars, the weight of atoms, the very possibility of matter itself. Imagine standing at the edge of understanding, where human curiosity meets the limits of the very small, where questions about the nature of reality require instruments larger than cathedrals, where the search for answers has consumed generations of minds, each one adding a piece to an ever-expanding puzzle. The story of particle physics is not simply a catalog of discoveries. It is a journey into increasingly subtle layers of existence, a gradual unveiling that began when ancient philosophers first wondered whether matter could be divided infinitely, or whether there existed some final, irreducible grain of substance, some fundamental unit beyond which nothing smaller could be found. For centuries, that question remained purely philosophical, a thought experiment conducted in the mind, without instruments, without mathematics precise enough to capture such minute scales. But as human understanding deepened, as tools became more refined, the question transformed from abstract speculation into something that could be tested, measured, answered through careful observation and brilliant reasoning. The particles we now know, the building blocks that construct protons and neutrons, the force carriers that mediate interactions, the elusive neutrinos that pass through entire planets without notice, these were once beyond imagination, unthinkable, and yet, through patience and ingenuity, they emerge from a shadow into the light of knowledge. There is something profoundly calming about contemplating these depths, about recognizing that beneath the complexity of daily experience, beneath the intricate machinery of biology and chemistry, there lies a simpler, more elegant set of rules, a handful of particles, a few fundamental forces, all interacting according to principles that can be written in equations, understood through symmetry, predicted with extraordinary precision. In this hidden world, time behaves strangely. Particles appear and vanish in fractions of a second, so brief that ordinary language struggles to contain them. Interactions occur across distances measured in femtometers, a scale so small that a million of them would barely span the width of a single human hair. And yet, within these infinitesimal domains, the character of everything is determined. The narrative we are about to explore unfolds slowly across decades and continents, through the work of thousands of researchers, each one contributing observations, theories, refinements to an ever-growing understanding. It is a story without a single hero, but rather a collective human endeavor, a conversation across time, where each generation builds upon the insights of those who came before. We will wander through this landscape gently, examining the particles themselves, the forces that bind them, the symmetries that govern their behavior, the experimental apparatus designed to reveal them, and the theoretical frameworks that predict their properties with astonishing accuracy. We will trace the emergence of this knowledge, not as a triumphant march, but as a patient accumulation of understanding, moment by moment, discovery by discovery, and as we move deeper, we will find that particle physics is not merely a technical discipline, but a meditation on existence itself, a way of asking what it means for something to be real, to be fundamental, to be necessary rather than contingent. These questions echo in the quiet spaces between particles, in the symmetries that seem almost too perfect to be accidental, in the mathematical beauty that emerges when nature is observed at its most basic level. So we begin at the threshold, where the visible world gives way to the invisible, where matter dissolves into energy and energy crystallizes into matter, where the dance of particles creates everything we know and everything we have yet to discover. The journey begins, as so many great journeys do, with the simple act of questioning what seems obvious. For most of human history, matter appeared solid, dependable, continuous. A stone was a stone. Water was water. And the idea that these substances might be composed of smaller, invisible units seemed either obvious or absurd, depending on the century and the culture asking the question. The ancient Greeks debated this puzzle with remarkable sophistication. Around 400 years before the Common Era, a philosopher named Democritus proposed that all matter consisted of tiny, indivisible particles he called atoms, from the Greek word atomos, meaning uncuttable. He imagined these atoms as eternal, indestructible, differing only in shape and size, tumbling through empty space, combining and separating to create the rich variety of substances we observe. It was a beautiful idea, born entirely from reasoning rather than experiment, and for nearly 2,000 years it remained just that, an elegant, dominant thought with no way to test its validity. Other philosophers disagreed, Aristotle among them, arguing that matter was infinitely divisible, that the notion of empty space made no sense, that the world consisted of continuous substances governed by qualities rather than discrete particles. His view dominated Western thought for centuries, not because it was proven, but because it aligned with the intuitions of experience, and because Aristotle's influence was so profound that questioning him seemed almost heretical. But ideas have a way of returning, especially when they resonate with something true about the nature of things. By the 17th century, as experimental methods began to replace pure philosophy, the atomic hypothesis started to acquire new life. Chemists noticed patterns in how substances combined. They observed that elements seemed to join in definite proportions, not in arbitrary amounts, as if some underlying discreteness governed their interactions. John Dalton, working in the early 1800s, revived the atomic theory with empirical support. He proposed that each element consisted of identical atoms, unique to that element, and that chemical reactions were simply rearrangements of these atoms into new configurations. His theory explained the observed ratios in chemical combinations, and though his atoms were still hypothetical, invisible to any instrument of the time, the explanatory power of the idea began to win converts. Still, many remained skeptical. The atom was, at this stage, more of a useful fiction than an established reality, a convenient accounting device that helped chemists keep track of reactions, but not necessarily a description of actual physical entities. The 19th century brought deeper mysteries. Physicists studying electricity discovered that it seemed to flow in discrete units. Michael Faraday's experiments with electrolysis revealed that charge itself appeared quantized, coming in fundamental portions rather than as a continuous fluid. This was peculiar, suggestive, a hint that perhaps the ancient intuition about discreteness in nature had merit after all. Then came the discovery that would crack open the atom itself, revealing it not as the final indivisible unit Democritus had imagined, but as a complex structure, a miniature cosmos with its own architecture. In 1897, J.J. Thomson, working at the Cavendish Laboratory in Cambridge, performed experiments with cathode rays, mysterious emanations that appeared when electrical current passed through evacuated glass tubes. By subjecting these rays to magnetic and electric fields, Thomson demonstrated that they consisted of particles, each carrying a negative charge, and each possessing a mass far smaller than even the lightest atom. He had discovered the electron, the first subatomic particle, the first proof that atoms were not indivisible after all, but contained smaller constituents. This was a threshold moment, a crossing from one understanding of matter to another. If atoms contained electrons, then atoms had internal structure, and the question immediately arose, what else might they contain, and how were these pieces arranged? Thomson himself proposed a model, sometimes called the plum pudding model, in which electrons were embedded in a diffuse sphere of positive charge, like raisins in a pudding. The positive and negative charges balanced, creating a neutral atom overall, but the internal dynamics remained mysterious. The true structure emerged through one of the most famous experiments in physics history, conducted by Ernest Rutherford and his colleagues Hans Geiger and Ernest Marsden between 1909 and 1911. They took a thin sheet of gold foil, only a few atoms thick, and bombarded it with alpha particles, helium nuclei ejected from radioactive material. If Thomson's model were correct, these massive, fast-moving alpha particles should pass through the gold atoms with only slight deflections, like bullets through fog. Most of the alpha particles did exactly that, but a small fraction, perhaps 1 in 8,000, bounced back at large angles, some nearly reversing direction entirely. Rutherford later said that this was the most incredible event of his life, as astonishing as if a shell fired at tissue paper had rebounded and struck the gunner. The only explanation, Rutherford realized, was that the atom's positive charge and most of its mass were concentrated in an incredibly tiny, dense nucleus at the center, with electrons orbiting at relatively vast distances. Most of the atom, it turned out, was empty space, and when an alpha particle happened to strike a nucleus head-on, the electromagnetic repulsion sent it careening backward. This nuclear model of the atom, published in 1911, transformed physics. Suddenly, the atom resembled a miniature solar system, with a massive central nucleus and lightweight electrons in orbit, but this picture immediately presented problems. According to classical electromagnetic theory, an orbiting electron should constantly radiate energy, spiraling inward and collapsing into the nucleus in a fraction of a second. Atoms should be unstable, yet they persisted, endured for billions of years, radiated light only under specific circumstances, and when they did, emitted only certain specific wavelengths, not a continuous spectrum. Something was profoundly wrong with the classical picture, or profoundly incomplete. The resolution came from an unlikely direction, from the radical idea that energy itself might be quantized. This concept had emerged in 1900 when Max Planck, studying the spectrum of radiation emitted by hot objects, found that he could explain the observations only by assuming that energy was absorbed and emitted in discrete packets, quanta, rather than continuously. Planck himself was uncomfortable with this conclusion, viewing it as a mathematical trick rather than a doctrinaire description of reality, but the idea proved remarkably fertile. In 1913, Niels Bohr applied quantum thinking to the atom. He proposed that electrons could occupy only certain allowed orbits, each with a specific energy, and that electrons could jump between these orbits by absorbing or emitting precise amounts of energy corresponding to photons of specific wavelengths. This explained the discrete spectral lines observed in atomic emissions. It stabilized the atom by declaring that electrons in allowed orbits simply did not radiate, a postulate that defied classical physics but matched observation. Bohr's model was a hybrid, mixing classical orbits with quantum rules in a way that was logically inconsistent, and yet it worked. It predicted the hydrogen spectrum with stunning accuracy, and it suggested that the quantum world operated according to principles fundamentally different from the everyday physics of motion and force. The atom, once thought indivisible, now revealed itself as a structured entity, containing a nucleus and electrons, governed by quantum rules that permitted only certain states. But the nucleus itself remained a mystery. What was it made of? How did it hold together? What determined which elements were stable and which decayed? Rutherford suspected that the nucleus contained positive particles, which he called protons, roughly 1,800 times heavier than electrons. The number of protons determined the element, hydrogen with 1, helium with 2, and so on up the periodic table, but the masses didn't add up. A helium nucleus, for instance, had 2 protons, but a mass roughly 4 times that of hydrogen, suggesting the presence of something else. Some additional neutral particles seemed necessary to account for the mass. This missing piece, the neutron, remained elusive for years, undetected because its lack of charge made it invisible to the methods that had revealed electrons and protons. It was not until 1932 that James Chadwick, also working at the Cavendish, definitively identified the neutron through careful experiments with beryllium radiation. Now the atomic nucleus had a clearer picture. Protons and neutrons, collectively called nucleons, bound together in an incredibly tight cluster with electrons occupying quantum states around this core. But binding nucleons together presented yet another puzzle. Protons carry positive charge, and like charges repel, the electromagnetic force should blow the nucleus apart, yet nuclei remain stable, often for billions of years. There had to be another force, something stronger than electromagnetism at very short distances, something that could overcome the electrical repulsion and hold nucleons together. This force, eventually called the strong nuclear force, operated only across distances comparable to the size of the nucleus itself, roughly a femtometer, but within that range, it was the most powerful force in nature. By the early 1930s, physics had descended beneath the atom, revealed the nucleus, identified three fundamental particles, the electron, the proton, and the neutron, and recognized that at least two fundamental forces governed their behavior, electromagnetism and the strong force. The picture seemed almost complete. Matter built from three types of particles, governed by understandable forces, but nature, as it turned out, was far stranger and far richer than anyone yet imagined. The first hint that the picture was incomplete came from the sky itself, from cosmic rays, high-energy particles that constantly rained down upon the Earth from space, streaming in from distant stellar explosions, from the sun, from sources still not entirely understood. In the 1930s, physicists began sending detectors aloft, carried by balloons into the upper atmosphere, and buried deep underground to study these mysterious visitors. What they found was bewildering. Cosmic rays, when they struck the atmosphere, created showers of secondary particles, and among these particles were things that didn't fit the known categories. In 1936, Carl Anderson, studying cosmic ray tracks in a cloud chamber, observed a particle that curved in a magnetic field exactly like an electron, but in the opposite direction. It had the same mass as an electron, but carried a positive charge instead of negative. This was the positron, the first antimatter particle ever detected, predicted just a few years earlier by Paul Dirac through purely theoretical reasoning. Dirac had been working on an equation to describe electrons in a way consistent with both quantum mechanics and special relativity, and his equation, beautiful and precise, produced two sets of solutions, one for particles with negative energy, which seemed nonsensical. Rather than dismiss these solutions as mathematical artifacts, Dirac proposed that they represented actual particles, mirror images of electrons with opposite charge. He called them anti-electrons. Though the name positron soon took hold, the discovery confirmed a profound principle that for every particle there might exist an antiparticle, identical in mass but opposite in charge and certain other properties. When particle and antiparticle met, they could annihilate, converting their entire mass into energy in accordance with Einstein's equation. Energy equals mass times the speed of light squared. This opened a strange new chapter. The universe now contained not just matter, but antimatter. And the question arose, why does our world seem built almost entirely from matter, with antimatter appearing only fleetingly in high-energy events, vanishing almost as soon as it forms? That question remains incompletely answered even now, but in the 1930s, it was merely one puzzle among many. More peculiar particles emerged from cosmic ray studies. In 1937, Anderson and Seth Nettermeyer found evidence of another particle, heavier than an electron but lighter than a proton. They called it a mesotron, later shortened to meson, and specifically, this was the muon. The muon was deeply confusing, and it seemed to be a heavier version of the electron, identical in every way except mass, unstable, decaying in about 2 millionths of a second into an electron and two neutrinos. It participated in electromagnetic interactions, but not in the strong nuclear force. The physicist I. Rabi supposedly quipped, "Who ordered that?" expressing the bewilderment of the community. The muon served no obvious purpose in building atoms, had no clear role in nuclear structure, and yet there it was, a redundant copy of the electron existing for reasons no one could immediately fathom. Nature, it seemed, was not as economical as physicists had hoped. Meanwhile, theorists were grappling with how forces actually worked at the quantum level. Electromagnetism had been successfully described by quantum electrodynamics. QED, a theory developed through the 1930s and 40s by Feynman, Schwinger, Tominaga, and others. In QED, forces arose from the exchange of particles, specifically photons, the quanta of light. When two electrons repelled each other, they did so by exchanging virtual photons, particles that existed only briefly, borrowing energy from the uncertainty principle, mediating the electromagnetic interaction before vanishing. This was a radically different picture from classical physics, where forces were fields that permeated space. Now forces themselves were quantized, carried by particles, transmitted through discrete exchanges. The strong nuclear force, logically, should work similarly, and in 1935, Hideki Yukawa proposed that nucleons were bound together by exchanging particles he called mesons, analogous to how photons mediated electromagnetism. But Yukawa's meson had to be massive to account for the short range of the strong force, roughly 100 to 200 times the electron's mass. When Anderson's muon was discovered, many initially thought it was Yukawa's particle, but the muon interacted too weakly. It passed through matter almost unimpeded, not behaving at all like the strong force carrier that theory predicted. The true Yukawa particle, the pion, was finally discovered in 1947 by Cecil Powell and his team, using photographic emulsions exposed to cosmic rays at high altitude. The pion came in three varieties: positively charged, negatively charged, and neutral, and it interacted strongly with nucleons, mediating the force that held nuclei together. Now the particle landscape was becoming crowded. Electrons, protons, neutrons, positrons, muons, pions, neutrinos. Each new discovery raised new questions. Were there patterns, families, underlying principles that governed which particles could exist? The situation grew more complicated throughout the 1950s. Physicists built increasingly powerful particle accelerators, machines that could smash protons and other particles together at high energies, creating conditions similar to those in the early universe, allowing new particles to materialize from pure energy. And particles appeared in abundance, strange new particles that decayed in unfamiliar ways, particles that seemed to violate expected symmetries, particles that appeared only in pairs, particles with lifetimes ranging from stable to almost instantaneous. The kaon, discovered in 1947, exhibited particularly odd behavior. It was produced copiously in high-energy collisions, suggesting it formed through the strong force. Yet it decayed slowly, as if governed by a much weaker interaction. This strange behavior led physicists to introduce a new quantum number called strangeness to classify these particles and predict their interactions. Then came the baryons, heavy particles, including the proton and neutron, but also many others. the lambda, the sigma, the psi, the omega, each with distinct masses and quantum properties, each fitting into families that suggested underlying patterns without revealing the pattern's origin. And the mesons multiplied. Beyond the pion, there were kaons, eta mesons, rho mesons, dozens of variants, all unstable, all decaying through various channels into lighter particles. By the early 1960s, hundreds of particles had been discovered, and the field faced a crisis of complexity. This couldn't be the fundamental level. It seemed inconceivable that nature required hundreds of elementary particles, each with arbitrary properties. There had to be a deeper layer, a more economical description. The breakthrough came from seeking patterns in the chaos. Murray Gell-Mann and Yuval Ne'eman independently proposed a classification scheme in 1961, organizing particles according to their quantum numbers, arranging them in geometric patterns they called the Eightfold Way, after the Buddhist path to enlightenment. These patterns had gaps, empty spaces where particles should exist if the symmetry was real, and in 1964, one of these predictions was spectacularly confirmed. The omega minus baryon, predicted by the pattern but never observed, was found in bubble chamber photographs at Brookhaven National Laboratory, with exactly the properties Gell-Mann had specified. This suggested that the symmetries were real, that particles were not arbitrary, but fell into families governed by deeper principles. But what created these patterns? What underlying structure could explain the Eightfold Way? Gell-Mann proposed an answer in 1964, one that seemed almost absurd at first. He suggested that protons, neutrons, and all other baryons and mesons were not fundamental at all, but were composed of even smaller entities he whimsically named quarks, borrowing a word from James Joyce's Finnegan's Wake. According to this scheme, there were three types of quarks, which he called up, down, and strange, each carrying a fractional electric charge, something never before observed. The up quark carried a charge of positive 2/3. The down and strange quarks each carried negative 1/3. A proton consisted of 2 up quarks and 1 down quark, giving a total charge of positive 1. A neutron contained 1 up and 2 down quarks, giving 0 charge. Mesons were quark-antiquark pairs, while baryons were combinations of 3 quarks. This model explained the Eightfold Way perfectly, predicted particle masses and quantum numbers, and reduced the hundreds of observed particles to combinations of just 3 fundamental constituents. But there was a problem. Nobody had ever seen a free quark, ever. Despite intensive searches, quarks appeared only in bound states, never in isolation. This seemed bizarre. If protons were made of the quarks, why couldn't you knock a quark loose? The answer, it turned out, lay in the peculiar nature of the strong force itself. Unlike electromagnetism, which weakens with distance, the strong force grew stronger as quarks were pulled apart, like a rubber band that becomes harder to stretch. Try to separate quarks, and the energy invested eventually becomes sufficient to create new quark-antiquark pairs, which bind with the original quarks, forming new composite particles, rather than freeing individual quarks. This property, called confinement, meant that quarks were permanently imprisoned within larger particles, observable only through their collective behavior, their combined quantum numbers and masses. Throughout the late 1960s and early 70s, The quark model gained acceptance, but it required modification. Deep inelastic scattering experiments where electrons were fired at protons at very high energies revealed that protons contained point-like constituents, confirming the quark hypothesis, but also showing that quarks themselves carried only about half the proton's momentum, suggesting something else was present. That something else turned out to be gluons, the carriers of the strong force itself. Just as photons mediated electromagnetism, gluons mediated the strong interaction between quarks, binding them into protons, neutrons, and mesons. But gluons had a unique property. Unlike photons, which carried no electric charge and thus didn't interact with each other, gluons carried a type of charge related to the strong force, a property called color charge, and gluons could interact with other gluons, creating a self-reinforcing field that grew stronger with distance, explaining confinement. The theory describing quarks and gluons, called quantum chromodynamics, or QCD, became the accepted description of the strong force, paralleling quantum electrodynamics but with crucial differences arising from gluon self-interaction. Meanwhile, the weak force, responsible for certain types of radioactive decay, was being unified with electromagnetism through the work of Glasgow, Weinberg, and Salam. They showed that at high energies, electromagnetism and the weak force were aspects of a single electroweak interaction, mediated by four particles, the photon and three massive bosons called the W+, W-, and Z0. These massive force carriers were predicted in the 1960s but not observed until 1983, when CERN's particle accelerator finally achieved sufficient energy to create them, confirming the electroweak theory and earning its architects the Nobel Prize. The structure was becoming clearer, but gaps remained, tantalizing hints that the picture was still incomplete. By the mid-1970s, physicists had organized their knowledge into what became known as the Standard Model, a comprehensive framework describing all known particles and three of the four fundamental forces. It was an extraordinary achievement, unifying decades of experimental discovery with elegant mathematical principles. The matter particles, the fermions, fell into two categories: quarks, which participated in the strong force and came in 6 types or flavors: up, down, strange, charm, bottom, and top, and leptons, which did not feel the strong force, including the electron, muon, tau, and their associated neutrinos. These 12 particles, 6 quarks and 6 leptons, arranged themselves into 3 generations, 3 families with identical properties except for mass. The first generation contained the up and down quarks, the electron, and the electron neutrino, the building blocks of ordinary matter. The second generation, heavier and unstable, included the charm and strange quarks, the muon, and the muon neutrino. The third, heavier still, contained top and bottom quarks, the tau and the tau neutrino. Why 3 generations? Why not 1 or 5? Nobody knew. The pattern suggested deeper structure, but the reason remained hidden. The force carriers, the bosons, included the photon for electromagnetism, 8 gluons for the strong force, and the W and Z bosons for the weak force. Each mediated interactions between matter particles according to specific rules, coupling strengths and symmetries. But even as this framework solidified, questions persisted. The most glaring concerned the origin of mass itself. In the Standard Model's equations, particles should be massless. Giving them mass by hand, simply inserting mass values into the equations, destroyed the mathematical consistency, violated the symmetries that made the theory work. Yet, obviously, particles had mass. Electrons, quarks, the W and Z bosons, all possessed definite masses measured to extraordinary precision. The resolution, proposed in 1964 by several physicists, including Peter Higgs, François Englert, and Robert Brute, involved a radical idea that empty space itself was not truly empty, but filled with an invisible field, the Higgs field, permeating all of reality. Particles acquired mass by interacting with this field. The stronger the interaction, the more mass the particle possessed. Photons, which didn't interact with the Higgs field at all, remained massless, while the top quark, with the strongest coupling, became the heaviest fundamental particle known. This was more than a mathematical trick. If the Higgs field existed, then quantum theory predicted it should have an associated particle, the Higgs boson, a quantum of excitation in the field itself. Finding this particle became one of the great quests of experimental physics, but it would require enormous energies to create, far beyond what any 1960s accelerator could achieve. The Higgs boson, if it existed, which was heavy, and creating heavy particles required enormous collision energies. Thanks again to mass energy equivalence, decades passed. Accelerators grew larger, more powerful, more precise. The Large Electron-Positron Collider at CERN, operational from 1989 to 2000, searched without success, ruling out lighter masses but unable to reach high enough energies to probe where the Higgs was most likely to hide. Meanwhile, other pieces of the Standard Model were falling into place with stunning conformations. The top quark, predicted by the pattern of generations but stubbornly absent from experiments, was finally discovered in 1995 at Fermilab's Tevatron Collider. It was extraordinarily heavy, about 185 times the mass of a proton, so heavy it decayed almost instantaneously, never forming bound states, existing only as a fleeting signature in detector data. The tau neutrino, the last of the Standard Model leptons to be directly observed, was confirmed in 2000, again at Fermilab, completing the roster of matter particles. But the Higgs remained elusive, its discovery waiting for a machine powerful enough, precise enough, capable of sifting through trillions of collisions to find the rare events where a Higgs boson briefly materialized before decaying into other particles. That machine, the Large Hadron Collider, began operations in 2008, built in a circular tunnel 27 kilometers in circumference, buried up to 175 meters beneath the Swiss-French border. It accelerated protons to 99.99999% the speed of light, smashing them together with energy 7 times greater than any previous collider. The scale was staggering. Superconducting magnets cooled to near absolute zero, detector systems weighing thousands of tons, millions of sensing elements recording particle trajectories, energies, identities, collaborations involving thousands of physicists from dozens of countries, analyzing petabytes of data, searching for subtle signatures against overwhelming backgrounds. And on July 4th, 2012, CERN announced the discovery, a new particle, consistent with the Higgs boson, observed independently by two different detector collaborations, ATLAS and CMS. Each had collected sufficient data to claim discovery, seeing an excess of events at a mass around 125 billion electron volts, exactly where a Higgs boson would produce such a signal. Further analysis confirmed the particle's properties, its spin, its decay modes, its couplings to other particles. Everything matched predictions. The Higgs field was real, the mechanism for mass generation confirmed, and the Standard Model was complete, at least in its particle content. This was a triumph, a validation of theoretical physics' power to predict phenomena decades before experimental confirmation. But it was also, in a sense, a disappointment. The Standard Model, for all its success, was clearly incomplete. It said nothing about gravity, the fourth fundamental force, which remained described only by general relativity, incompatible with quantum mechanics at fundamental levels. Attempts to create a quantum theory of gravity had produced mathematical infinities, problems with renormalization, obstacles that decades of effort had not overcome. The Standard Model could not explain dark matter, the invisible substance that dominated the mass of galaxies, outweighing ordinary matter by factors of 5 or 6. Astronomical observations left no doubt that dark matter existed, and yet none of the Standard Model particles fit its properties. It had to be something new, something beyond the known roster. Nor could the Standard Model account for dark energy, the mysterious component causing the universe's expansion to accelerate, making up roughly 70% of the total energy density of the cosmos. This was completely outside the framework, unexplained, barely even addressed. The matter-antimatter asymmetry remained puzzling. The Standard Model predicted some asymmetry through CP violation in the weak force, but not nearly enough to explain why the universe contained matter and essentially no antimatter. Some additional mechanism, some new physics, seemed necessary. Neutrinos, once thought massless, had been shown through oscillation experiments to possess tiny but non-zero masses. They changed flavor as they traveled, electron neutrinos becoming muon or tau neutrinos and back, a quantum phenomenon requiring mass differences. Yet the Standard Model had no mechanism to give neutrinos mass, at least not in its original formulation, and there were aesthetic issues. 25 free parameters, masses and coupling strengths that had to be measured rather than predicted. Why did the top quark have one mass and the electron another? Why were the forces' strengths what they were? The Standard Model described these values but didn't explain them. Many physicists suspected that the Standard Model was an effective theory, accurate within a certain energy range, but ultimately an approximation of something deeper, more fundamental. Just as Newtonian mechanics emerged as an approximation to relativity at low speeds, perhaps the Standard Model emerged from a more complete theory at energies higher than current accelerators could reach. Theories beyond the Standard Model proliferated. Supersymmetry proposed that every fermion had a bosonic partner and vice versa, doubling the particle content but potentially explaining dark matter and stabilizing the Higgs mass. String theory suggested that particles were not point-like, but tiny vibrating strings, with different vibration modes corresponding to different particles, unifying all forces, including gravity in a 10 or 11-dimensional framework. Extra dimensions, grand unified theories, technicolor, prion models, each offered potential solutions to some problems while introducing new questions, new predictions, new levels of complexity. But experiments at the Large Hadron Collider found nothing beyond the Higgs. No supersymmetric particles, no extra dimensions, no unexpected resonances. The data matched standard model predictions with almost unsettling precision, leaving physicists in the strange position of having a theory that worked beautifully but remained deeply unsatisfying. The frontier had shifted. No longer were physicists discovering new particles every few years. Instead, they refined measurements, constrained possibilities, searched for tiny deviations from predictions that might hint at new physics, looked to rare decays, subtle asymmetries, anomalies in muon magnetic moments or B-meson decays. And they looked outward to neutrino detectors buried in Antarctic ice or deep in Japanese mines, to gravitational wave observatories detecting ripples in space-time from colliding black holes, to dark matter detectors waiting in abandoned mines for the rare interaction of a dark matter particle with ordinary matter. The questions had changed from what particles exist to what lies beyond what we know, from discovering the next layer to understanding why this layer has the structure it does. Particle physics had reached a curious plateau. The standard model reigned supreme within its domain, tested to exquisite precision, confirmed in thousands of measurements, and yet everyone knew it was incomplete, a chapter in a longer story whose next pages remained unwritten. The field settled into a new rhythm, building more sensitive detectors, conducting longer experiments, analyzing data with greater sophistication, searching for the subtle, the rare, the unexpected, waiting for nature to reveal the next clue, the next anomaly that would point toward deeper truths. And in this waiting, in this patient observation, there emerged a different kind of understanding, not of new particles, but of the achievement already realized, the profound knowledge already won. From this vantage point, with the landscape of particle physics spread before us like a completed map of terra incognita, certain patterns emerge that transcend the mere catalog of particles and forces. There is first the recurring theme of symmetry, woven through every level of understanding. Symmetries dictate which interactions can occur, which conservation laws must hold, which particles can transform into others. The mathematics of symmetry, group theory, becomes the language through which nature's preferences express themselves. When a theory possesses a symmetry, something remains unchanged under transformation, rotate space, and the laws of physics remain identical. Shift time forward or backward, and the equations hold their form. These symmetries, so abstract in mathematical expression, manifest as conservation laws, energy, momentum, angular momentum, the bedrock principles that govern every interaction. But particle physics revealed deeper symmetries, internal symmetries unrelated to space and time. The strong force, for instance, treats all quark colors identically: red, green, blue, arbitrary labels for symmetry that ensures gluons couple to color charge regardless of which color a quark carries. This SU3 symmetry, as mathematicians call it, generates the 8 gluons and determines their interactions. The electroweak force emerges from another symmetry, SU of 2 times U of 1, relating the electromagnetic and weak interactions, showing them as facets of a unified whole, only appearing separate because the symmetry is hidden, broken by the Higgs field, like a perfectly symmetric vase that falls and shatters. The pieces remember their origin, retain traces of the original form, but the symmetry is no longer manifest. This breaking of symmetry, this transition from unified to separated, likely occurred in the early universe when temperatures dropped below a critical threshold and the Higgs field acquired its non-zero value, condensing throughout space like dew forming on grass at dawn. In that moment, the unified electroweak force split. Particles acquired masses, and the universe took on the character we observe today. There is something profound in this, the apparent complexity, the different forces with different strengths and ranges, the hierarchy of particle masses. All this diversity emerges from symmetry breaking, from a kind of cosmic phase transition. The underlying reality is simpler, more unified, but hidden beneath the broken symmetry we inhabit. And then there is the matter of scale, the extraordinary range of magnitudes that particle physics encompasses. A proton measures roughly 1 femtometer across, 1/quadrillionth of a meter. Inside that proton, quarks are confined to even smaller scales, effectively point-like as far as experiments can tell, possibly smaller than 10 to the minus 19 meters, a billionth of a meter. Yet to study these infinitesimal objects, we build machines of enormous scale. The Large Hadron Collider's 27-kilometer ring, its thousands of magnets, its hundreds of millions of sensor channels, its energy budget matching a small city's, all this to probe distances so small that light itself crosses them in times measured in yoctoseconds, septillionths of a second. The disproportion seems almost comical, and yet it reflects a deep truth about nature. To see smaller, you need higher energy. Higher energy requires stronger fields, bigger accelerators, more elaborate detectors. The frontier of the small demands instruments of the large, linking the study of fundamental particles to engineering projects of monumental ambition. And there is the peculiar relationship between the very small and the very large, between particle physics and cosmology, the conditions that existed in the first moments after the Big Bang, when the universe was unimaginably hot and dense, can be recreated briefly in particle collisions. The quark-gluon plasma, a state of matter where quarks and gluons roam freely rather than being confined in protons and neutrons, existed throughout the cosmos for the first few microseconds, and now exists again for fleeting instants in heavy ion collisions at CERN and Brookhaven. The Higgs mechanism, which gives particles mass, operated differently in the early universe. At sufficiently high temperatures, the Higgs field vanished. Symmetry remained unbroken. Particles were massless. Only as the universe cooled did the field condense, the symmetry break, masses appear. Understanding particle physics thus becomes a way of understanding cosmic history. The relative abundances of elements, the cosmic microwave background radiation, the large-scale structure of galaxies, all these depend on particle interactions in the early universe, on cross-sections and decay rates and coupling constants measured in modern laboratories. We look inward to the smallest scales and find ourselves looking backward to the earliest times. The microscope becomes a telescope, peering not across space but across time, to moments when the universe fit within a volume smaller than an atom, when all the matter and energy we observe today existed in a state of almost incomprehensible density and temperature. There is also the role of uncertainty, not merely as experimental error, but as fundamental principle. Heisenberg's uncertainty principle, the impossibility of simultaneously knowing both position and momentum with arbitrary precision, manifests throughout particle physics. It allows virtual particles to appear, borrowing energy for brief moments, mediating forces before dissolving back into the quantum foam. It permits quantum tunneling, where particles cross barriers they classically shouldn't penetrate, enabling nuclear fusion in stars and radioactive decay in unstable nuclei. The quantum vacuum, far from being empty, seethes with virtual particles, particle-antiparticle pairs constantly appearing and annihilating. The energy of this vacuum, calculated naively, comes out absurdly large, 120 orders of magnitude larger than the observed dark energy density. This vacuum catastrophe, this spectacular failure of prediction, remains one of physics' most embarrassing unsolved problems. And yet, the quantum vacuum has measurable effects. The Casimir effect, where two uncharged metal plates attract due to modified vacuum fluctuations between them, the Lamb shift, a tiny energy difference in hydrogen's spectrum caused by electron interactions with virtual photons. These confirm that the vacuum is not nothing, but a dynamic, fluctuating medium. Particle physics thus reveals a universe that is never still, never truly empty, never fully determinate, a universe where observation affects reality, where particles exist in superposition until measured, where the act of detection collapses possibility into actuality. Finally, there is the human dimension, easily overlooked amid equations and detector specifications. Thousands of physicists collaborate on single experiments, sharing data, co-authoring papers with author lists that scroll for pages. Their work requires patience, building detectors over decades, taking data for years, analyzing events that occur perhaps once in a trillion collisions. They develop new technologies that ripple outward into society: superconducting magnets, advanced computing, particle therapy for cancer, medical imaging, grid computing, the World Wide Web itself, invented at CERN to help physicists share data. All this emerges from the quest to understand nature's fundamental structure, and they pursue knowledge for its own sake, driven by curiosity about how things work, what the world is made of, why reality has the form it does. These questions have no immediate practical application, no quarterly earnings impact, no 5-year strategic value, and yet they represent something essential about human nature, the impulse to understand, to question, to seek patterns in apparent chaos. The story of particle physics is thus also a story about what it means to be human, to ask questions whose answers require generations to unfold, to build collaborations across borders and languages, to seek truth in the face of uncertainty, to pursue beauty in mathematical structure, to find meaning in understanding. And so we return to where we began, to the invisible realm beneath the surface of things, now perhaps with different eyes. The particles dancing in the quantum foam, the quarks confined within protons, the neutrinos streaming through the earth, the Higgs field permeating space, all these continue their ancient patterns. indifferent to observation, governed by laws that permit no exceptions, the electrons flowing through the circuit of the device reading these words, the quarks in the atoms of your body, the photons carrying signals, all participants in the same quantum dance described by the Standard Model, all following rules discovered through decades of patient inquiry. There is a kind of peace in this understanding and recognizing that beneath complexity lies pattern, beneath diversity lies unity, beneath apparent chaos lies mathematical order. The universe, at its deepest explored level, consists of 12 matter particles, 4 force carriers, and 1 scalar boson, all interacting according to principles of symmetry and quantum mechanics. From this sparse inventory, everything emerges: atoms and molecules, chemistry and biology, stars and galaxies, consciousness and thought. We are quite literally made of particles whose properties were unknown a century ago, whose very existence was unsuspected for most of human history. The atoms in our bodies contain quarks that have been confined since the early universe, electrons that will outlast the stars. We are temporary patterns in a sea of quantum fields, arrangements of fundamental particles held together briefly by forces now understood in exquisite detail. And yet, for all this understanding, mystery remains. The Standard Model, complete in its domain, points beyond itself, hints at deeper structures, suggests questions it cannot answer: dark matter and dark energy, gravity and quantum mechanics, the hierarchy of masses, the number of generations. All these await explanations not yet found. Perhaps future accelerators will reveal new particles, new forces. Perhaps observations of cosmic rays or neutrinos or gravitational waves will provide the crucial clues. Perhaps the next breakthrough will come from unexpected directions, from mathematical insights or astronomical observations or careful reconsideration of existing data. Or perhaps we have reached the limits of what particle colliders can teach us. Perhaps the next layer lies at energies forever beyond our reach. Perhaps we must learn to extract truth from precision rather than discovery, from subtle measurements rather than dramatic new particles. Either way, the journey continues, the questions evolve, the patient work proceeds. In laboratories scattered across the world, detectors wait in the darkness, recording the rare, the subtle, the unexpected. Superconducting cavities accelerate particles to nearly light speed. Magnets bend their paths into collisions. Electronics capture the debris. Computers reconstruct events. Physicists analyze patterns, searching always for the anomaly, the deviation, the hint of something new. And in the quiet spaces between measurements, in the pauses between collisions, in the gaps between one discovery and the next, there is simply the particles themselves, existing as they always have, governed by principles that precede human understanding and will outlast it. The quarks and leptons, the bosons and fields, the symmetries and interactions, all continue their eternal dance, indifferent to names we give them, unconcerned with our theories, simply being what they are, following the rules written into the structure of reality itself. We have glimpsed that structure, traced its outlines, measured its parameters, built models that predict and explain, and in doing so, we have touched something fundamental, something true, something that transcends the particular moment and speaks to the underlying nature of everything. This is what particle physics offers: not certainty, not completion, but a map of the deepest territory yet explored, a description of the foundations upon which everything rests, a glimpse into the quantum realm where reality reveals its most basic character. And now, as the words slow, as the journey through the particle landscape draws towards its end, we can rest in that knowledge. Let it settle. Allow the patterns and principles to fade gently into the background, like stars disappearing at dawn, still present, still real, but receding from immediate view. The particles remain, doing what they have always done and what they will always do, existing at scales beyond sight, following laws beyond everyday experience, building from their simple interactions the entire complexity of the observable universe. And we have followed them into that hidden realm and returned, carrying with us perhaps a sense of wonder, an appreciation for the depth beneath the surface, and a quiet recognition that reality, at its foundation, is stranger and more beautiful than we ever imagined. The quantum fields vibrate on, the forces mediate, the symmetries hold, and the universe continues particle by particle, interaction by interaction, moment by moment, as it has and as it will, in patterns now partly known, partly understood, and partly still wrapped in mystery.